Good afternoon, class. Here's exam to review chapter 3, differentiation rules. Chapter 4, application of differentiations. Exam 3 covers from 3.9 to 3.11 and 4.1 to 4.5. And so now we have how derivatives affect the shape of a graph, indeterminate forms, and L'Hopital's rule, summary of curve sketching. So 4.3, the theorem, how derivatives affect the shape of a graph. A function is increasing where f prime is positive and decreasing where f prime is negative. So increasing looks like a line with a positive slope. Decreasing looks like a line with a negative slope. Definition, a critical point C of a function is a point of which f prime of x equal to 0 or f prime dne does not exist. Definition, a relative maximum or relative minimum is a critical point at the top or bottom of an interval of a graph. Peaks and valleys. Theorem, a function is concave up where f double prime is positive. That means f prime is increasing, and it's concave down where f double prime is negative, meaning f prime is decreasing. So concave up, like it can hold water, and concave down cannot. And an inflection point C is a point where concavity changes. Inflection points occur where f double prime is 0 or f prime does not exist. And looking like that, this is the point where this function is concave up here, then changes to concave down. Point where the change occurs is the point that we are referring to as the inflection point. To graph, I want to remind you of a couple of interesting things from algebra. Recall the end behavior of a polynomial function is the behavior of the graph of f of x as x approaches positive infinity or negative infinity. The degree and the leading coefficient of a polynomial function determine the end behavior of the graph. A polynomial is in the form of a sub n x to the power of n. F of x equals a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1 all the way to a sub 0. This is called the leading term. So ultimately, it will look like the leading term a sub n x to the power of n. So what happens is that if it's even power, and a sub n, the leading coefficient is positive here, looks like that. If it's odd power, looks like that, meaning the end behavior looks like the y equals x squared or y equals x cubed, depending upon the value of a sub n. If it's negative, looks like minus x squared and minus x cubed in the case of a odd power. And when we say x goes to negative infinity, f of x goes to infinity, that's the, second quarter. When x goes to infinity, f of x goes to infinity, that's the first quarter. This one, negative goes to negative, positive goes to positive infinity, first and third quarter. And the rest of it, just to remind you of the end behavior. X goes to negative infinity, so does y. X goes to infinity, f of x goes to negative infinity. Bear in mind, f of x refers to the y coordinate. So that means the third and fourth quadrant. X goes to negative, y goes to infinity, x goes to positive infinity, y goes to negative infinity, looking like minus x cubed, the second and fourth quadrant. Also, there's a behavior near a zero multiplicity m. Recall x minus c to the power of m. That means it has a multiplicity m. If m is odd, f crosses the x-axis at c0. If it's even, it can't cross the x-axis. So looking like that for the case of odd, okay, in this case, there's a single zero in all of them, okay, 0, the multiplicity of 2 because it bounces back, and it becomes flatter, okay, if we have a higher multiplicity. So in general, The higher the multiplicity, the flatter the curve is at the zero. The sum of the multiplicities is the degree of the polynomial function. So this was a short reminder of what we do when it comes to graphs and so forth. We want to graph f of x equals minus x cubed times x squared plus x. So the idea is that what are the steps in curve sketching? In addition to algebra, slash pre-calculus steps, all the steps that we get there, okay, like intercepts and so forth, the end behavior, the behavior near an x-intercept, all of the above. Then we add, find relative max and mean and intervals where the function increases and decreases. That means set f prime equal to 0 and solve for x and make a sign graph. Number 2, find inflection points if we have any. That means f double prime of x, solving for x, make a sign graph. Find IPs, inflection points. IP short for inflection points and a concavity. Sketch the graph, put them all together. So one of the things we are going to do is to find the intercepts, everybody. And let's first factor the x out, or better yet, minus x. We want to put it in descending order. That gives us minus x times x squared minus x minus 1. By the way, the y-intercept clearly is 0, 0. So replace the x with 0, you get 0. So it's easy to find the y-intercept. Or if you look at this one, x is 0. We want to find all the x-intercepts. So x is 0, y is 0. You set this one equal to 0, and it can use the quadratic formula, because b squared minus 4ac is not a perfect square. So in this case, okay, we are going to use the quadratic formula. And in this case, I'm going to write, we are dealing with this one, okay, where a is 1, b is negative 1, c is negative 1. We put it into the quadratic formula. It's minus b. So minus negative 1 makes it 1, plus minus the b squared negative 1 quantity squared minus 4 times a times c over 2 becomes 1 plus minus square root of 5 over 2. In other words, the intercepts are the following three: 0, 0, which is both x and y intercept, 1 plus square root of 5 over 2, 0, and 1 minus square root of 5 over 2, 0. So those are the intercepts. And believe it or not, you have an idea how to graph this just with those if you want. So I want to graph this using pre-calculus. Then I'm going to add calculus to that. So if I want to stick with that, and by the way, when b squared minus 4ac is a perfect square, that means you can factor. Remember, when it's negative, has no real solutions. When it's 0, it has a double root. And so just to give you an idea, as far as the end behavior is concerned, it looks like minus x cubed. So that's the end behavior, everybody. Okay. So the second and the fourth quadrant. So this is the leading term. So leading term is minus x cubed. So it looks like that's the end. Now we have the intercepts. This is 0, 0. And for 1 plus square root of 5, so we end up with square root of 5 is a little bit more than 2, because square root of 4 is 2. It's about roughly about 2.4, 2.5, and you add to 1, 3.23 divided by 2, close to 1.6. Okay, so and I say that because of the graphing. So let me say this one is roughly, and it's not perfect, 1.6, 0, and that makes this one 1 minus that divided by 2, about roughly minus 0.60. I'm doing this for the sake of graph. So if I have 1 here and 2 here and -1 here and -2 here, then I use a different color and I say, okay, this is 0, 0, and this is 1 point roughly. It's not perfect. 1.60 here and -0.60 here, and here's my end behavior. Okay, so if I hit this point, this x-intercept, it crosses it because all of them has multiplicity equals 1 for each and every one of those zeros. So it crosses it, has to come back up at some point, hits the other one, goes back up, has to come back down at some point and hits the third one. So this is 1, 2, 3 different intercepts. It's not exact. You may not know exactly where it comes back. In other words, the local mean, local max, exact location of the IP, because this is concave up, then it becomes concave down, but that's good. It's a rough sketch. This is pre-calculus. What we are going to do, we are going to make it look better with more details. So I'm going to erase my work. The purpose of that was to show you, okay, we could still graph it using prior knowledge of calculus. So, all right, so the next step is to find f prime of x. We are going to differentiate. This one is easier. Minus 3x squared plus 2x plus 1, and we are going to set it equal to 0. To do that, we are going to factor the negative out. So we get minus 3x squared minus 2x minus 1. And since 3 is a prime number, makes it very easy to factor. You have to go with 1 and 3. And of course, -1, you have to go with 1 and 1. One of them negative, and you end up with this. So f prime being 0 gives you two possibilities. X is either 1 or -1/3. So we have all the CPs, critical points. Now, we need to find where the function is increasing and decreasing. We are going to do the first derivative test, and we have to use the sine graph. So what we are using here is the sine graph. So what do? Here's the number line, goes from negative to positive infinity. You put those critical points here at -1/3. See, the bottom is x, the top is f prime. At -1/3, f prime is 0. As positive at +1 also, that is 0. So that's something to pay attention to. And now, by the way, you pick a test point, but please understand that they have to alternate because this has degree 1, this has degree 1. If the degree is odd, they will alternate. If any of them is even, both sides would be the same. So you pick TPs. TPs, short for test points. So over here, like -1, between negative and positive, the easiest would be 0. After 1, let's say 2. And you put that into f prime. If it's easier, use this one. If it's easier, use the factored form. Because all you want, is it positive or negative? That's all. So I'm going to go with the easiest one. If I put the 0 and I put it here, it's +1. So this is positive and they alter. But if I want to check it, I put -1 into this one or this one. It might be easier to put it into this one. If I put -1 here, this becomes negative. This becomes negative. Their product is positive, but this makes it negative. So this is negative. Can plug in 2 and try it. But like I said, in the middle is positive. The rest of them negative. What does it mean? Let's throw in arrows. This means negative means decreasing, positive means increasing, negative means decreasing. As it changes from decreasing to increasing, decreasing to increasing, think about parabola, decreasing to increasing, that is a local mean, okay? And then from decreasing to increasing, that means, okay, from increasing to decreasing, that means, look at the arrow, local max. And what you have to do, you have to plug in those two values into the original function to find the y coordinate at x equals -3, x equals 1. Also, it's increasing where it says positive. That means from negative 1/3 to 1 is increasing. Here and here is decreasing. That means from negative infinity to negative 1/3, union 1 to infinity. So local max is equal to 1 at 1 comma 1. How do we get that? Put the 1 in here or here. Maybe easier to put it here. If I put 1 here, I get positive 1 with the negative becomes negative, cancels this one, positive 1. So again, I'm going to put negative 1/3 in there. In fact, I'm going to show you because I want you to know you have to put it back into the original function and evaluate. If I minus 1/3, so negative remains, negative 1/3 cubed plus negative 1/3 squared minus 1/3. This one becomes negative 1 over 27. This makes it positive. This square makes it positive. And I hope you recognize 27 as a common denominator. So this is 1, this is 3, and this is minus 9. They add up to minus 5. I'm assuming we have no problem with fractions. So local mean is the y coordinate, minus 5 over 27 at the pair. And I already mentioned the increasing, decreasing, increasing in the plus area in this vicinity. Otherwise, would be decreasing. So we got a lot of information that will help us with the graphing, everybody. So we found this part. Now we're going to go with the inflection point. That means I'm going to remind you, this is what we found in the previous page. Here's the F, here's the F prime. Now we're going to go with the IPs, and therefore I'm going to go with F double prime and set it equal to 0. To do so, here's F prime. So F double prime would be minus 6x plus 2. Again, these are information from the previous page, everybody, okay? I didn't want anybody to miss those. And so F double prime is negative 6x plus 2. And if you set it equal to 0, I hope everybody can see that if you set it equal to 0, it becomes 1/3. Just quickly set this equal to 0, 2 equals 6x, and x equals 1/3. Very simple. We do a sign graph. And so what happens is very simple. X goes from negative to positive infinity. And we put where F double prime is 0 there. And at top is F double prime. At 1/3 is 0. We are interested in the left and right. So to the left of 1/3, you pick a negative number. Or even easier, 0. And to the right, you pick like 1. So and again, they are going to alternate. It's just 1. If you plug in 0, here, you get positive. So this is positive. The other one must be negative. Again, they alternate, class, okay? Let me clean up my mess and then do it again. So the test point that I used here is 0 TP. You can test the one, but you don't have to. If you test it, you see that becomes negative. So what does it mean? Here's what we want to discuss. It means over here is concave up from negative infinity to 1/3. Over here is negative, means concave down from 1/3 to infinity. I hope everybody is following that. And then because of the change, if there's no change, meaning both of them are positive or both of them is negative, so be it. Otherwise, this is the point known as IP, the inflection point. So if the inflection point takes place at 1/3, what is its y coordinate? You have to put it back into the original equation, f of 1/3. So you raise this to the power of 3, you get negative. You get positive 1 over 27. With this becomes negative. This becomes 1 over 9. This is 1 over 3. The common denominator is 27. So this is 3 over 27. This is 9 over 27. With a negative 1, they add up to positive 11 over 27. And so the IP has the coordinates 1/3 and 11 over 27. Let's write a summary of what we found. The x-intercept is at 0, 0. Also add 1 minus square root of 5 over 2, which is negative 0.620. And again, we write it in this format for the sake of graphing. Also 1.620, the maximum at 1.1, IP address, minimum, maximum. So let's put those 0.00, negative 0.620, roughly here 1.620. By the way, like I said, it crosses each of them, each and every one of them. In some cases, it may bounce. In this case, it doesn't happen. Maximum occurs at 1.1, and we put the arrow here just to indicate that its maximum, it can't cross it. The IP occurs at this exact pair, and because we want to graph it, about 0.33 and 0.41 is here. The minimum occurs at negative 1/3, negative 5 over 7. Again, because we want to graph it, we go with the decimal, so that would be the location, and we put an arrow, meaning it can't cross that. We've already discussed the end behavior, so it looks like that. Of course, it's a lot more exact because we added a lot of information from calculus. Four point four, indeterminate form and L'Hopital's rule. Limits of the following forms are indeterminate forms. An indeterminate form of type 0 over 0, infinity over infinity. And there are a lot more, but what is the meaning of it? The meaning of indeterminate form, as we've been discussing, is that there is more work to be done, class. So there are various techniques to handle it, okay? And one of the techniques that we are adding is L'Hopital's rule. So these are some examples of indeterminate form. The limit of ln x over x minus 1 as x approaches 1 is 0 over 0. The limit of ln x over x minus 1 as x approaches infinity is infinity over infinity. So according to L'Hopital's rule, suppose that f and g are differentiable and g prime is not equal to 0 on an open interval that contains a except possibly at a. Suppose that the limit of f of x as x approaches a is 0, and limit of g of x as x approaches a equal to 0. Or that the limit of f of x as x approaches a is positive, negative, infinity. In other words, we have the indeterminate form of 0 over 0, infinity over infinity. In that case, we can use the L'Hopital's rule, which says the limit of f of x over g of x as x approaches a is the same as taking the limit as x approaches a of f prime over g prime. So it is not a quotient rule, don't mix them up. What it says take the derivative of the top, put it at top, take the derivative of the bottom, put it at the bottom, and now take a limit. That's all there is to it, okay? Now you work on it, it gives you an answer or it doesn't. If it gives you the same situation, you do it again and again and again. So in short, the limit of f of x over g of x as x approaches 0. If it's 0 over 0 or infinity over infinity, you can use L'Hopital's rule. Okay? So that's L'Hopital's rule. Indeterminate products, indeterminate form of type 0 times infinity. Rewrite the product fg as f over 1 over g or g over 1 over f and make it look like 0 over 0 or infinity over infinity and work on it. That's all there is to it. Here's an example that we wrote. Before I use the L'Hopital's rule, I have to write down the answer. I have to write down, if I plug in 1, let me show you. I get ln 1 over 1 minus 1, which is 0 over 0. If you don't show that, you cannot use the L'Hopital's rule. This is, I can't emphasize this enough. First, you show that it's either 0 over 0, infinity over infinity, then you move on. Now, the notation that they put, sometimes they put H, sometimes they put equality with H at top. That means they're using the L'Hopital's rule. So that means I'm going to take the derivative of the top, which is 1 over x, and the bottom is 1. And I'm using the L'Hopital's rule, okay? And that's very straightforward, everybody. If I plug in and it works out, I'm done. First and foremost, this is 1 over x. Secondly, now if I plug in, I get 1 and I'm done. Yes, that's it. This one, what's the answer? First, let me plug in and observe. So if I plug in, I get e to the power of 0 minus, let me actually put it here so I don't have to erase it. Let me erase the whole thing and then. So I get e to the power of 0 minus e to the power minus 0 is the same thing. Minus 2 times 0 over 0 minus sine 0. I hope you realize this is 1 minus 1, which makes it 0, minus 2 times 0, which makes it 0. Sine of 0 is also 0, so you get 0 over 0. So you prove it's 0 over 0, therefore you can use L'Hopital's rule. So I'm going to differentiate the top. I get e to the power of x. I get minus times minus plus e to the power of x, minus 2. And this is 1 minus cosine x. And don't forget to carry the limit. And I'm telling my readers I used L'Hopital's rule. Plug in. Again, I want to show what I get. If I plug in, I get e to the power of 0 plus e to the power minus 0, which is the same as 0, minus 2 over 1 minus cosine 0. Cosine 0 is 1, so the denominator is 0. This is 1, this is 1, adds up to 2, minus 2 is 0. Again, 0 over 0. Again, I'm going to use the L'Hopital's rule. First, show and prove it's 0 over 0, or infinity over infinity for that matter. So you have differentiate this one, e to the power of x plus e to the power minus x times negative 1. That means minus e to the power of x. This goes away. Cosine gives you negative sign, with this becomes positive. Let's plug in. Now I get e to the power of 0 minus e to the power of 0 over sine of 0. The top is 1 minus 1. The bottom is 0. And I'm going to use L'Hopital's rule again. So e to the power of 0. So I hope you see that e to the power of 0 minus e to the power of 0, they cancel each other, they become 0. And this is sine of 0, which is 0. So the derivative is e to the power of x. Minus minus plus e to the power minus x. Sine gives you cosine. Don't lose the lim sign. Now let's plug in. Let's use a different color. So if I put e to the power of 0 plus e to the power minus 0, that means again the same thing, and I put cosine of 0, I hope you recognize this as 1 plus 1 over 1. So the answer is 2, and now I'm done. Okay. That's the idea, everybody. What about this one? Plug in power 2. So put okay, let me actually erase everything. So 1, I plug in 1 minus sine of power 2 over cosecant. I don't want to go with cosecant. I'm going to go with 1 over sine because I know the sine, okay? You know that sine of power 2 is 1. So the top is 1 minus 1 is 0, and the bottom is 1 over 1 is 1. So 0 over 1. Class, the numerator is 0. The denominator is 1. And it's done. The answer is 0. So please understand it's not indeterminate, okay? What about this one? If I plug in 2, let's see if I can quickly show that. Obviously, the denominator is 0. 2 squared is 4, and 2 minus 6 is 0 over 0. Again, you have to show that if you, if you think it's 0 over 0, quickly calculate it and show that. There are different techniques. One of them is L'Hopital's rule, and one of them is what we did before. We could factor the top into x minus 2 times x plus 3. And now if I plug in 2, I get 5. I'm going to show you with L'Hopital's rule, okay? If I want to go with L'Hopital's rule, it becomes the limit of 2x plus 1 over 1, or the limit of 2x plus 1. And x is approaching what number? 2. X is approaching 2. If I plug in 2, I get what? 5 in both cases, okay? So whether I go with the L'Hopital's rule or the old method that was factoring, it will give me the same answer. Okay, both methods, L'Hopital's rule, old method. We want to plug in, and when we plug in ln of infinity or square root of infinity, makes no difference, is infinity. The bottom is infinity, squared is infinity. Infinity over infinity, that means I can use L'Hopital's rule. That means I'm going to differentiate the top, differentiate the bottom. And to differentiate the top, I have 2 ways. I'm going to quickly go over one method, and then I'll show you the easier method. The way it is, remember, you have to flip this over, right? 1 over square root of x. And then the derivative of that, by now, you may know it's 1 over 2 square root of x. And of course, x squared gives you 2x. But the easier way would have been class ln of x to the power of 1/2, and therefore half of ln x over x squared. And if you go this route, 1/2 remains. You can put the 2 down here, or you can say ln x over x squared. And this gives you 1 over x. But anyways, let's continue. Either way, 1/2 times 1 over x over 2x. Okay, you can write it in this fashion. Or if you go here, it's 1 over so the numerator is 1 over 2x, and this is a complex fraction, becomes 1 over 4x squared. I hope you see that. Whether you look at this one or this one, both of them will give you 1 over 4x squared. And as x approaches infinity, the top is a number, the bottom is infinity, the answer is 0. I would have preferred using this one, class, because that simplifies the work, and you have to know how to decompose logarithmic and use logarithmic properties to decompose. Find the limit of x times ln x as x approaches 0 from the right. And the reason is from the right because natural log, the domain is from 0 to infinity. And I hope you recognize you can just multiply x by ln x. So what is this? You plug in becomes 0. This becomes minus infinity. I want to make sure that you remember this graph, everybody. This is y equals ln x roughly. So therefore 0 times negative infinity. And so what do we do in that case? Reminding you, if we have 0 times infinity, rewrite it as f times g as a quotient. So f times g is f over 1 over g, or g over 1 over f. In this case, it's easier to take the x down and write it 1 over x. Now, the top is minus infinity. If I plug in, because ln of 0 from the right, see, minus infinity. And the bottom is positive infinity, because 0, x is approaching 0 from the right. So now we are going to use L'Hopital's rule. The top gives you 1 over x, and the bottom by now it's negative 1 over x squared. If you don't know that, if you don't, you should show the work, but this one, you write it as x to the power of minus 1, and then when you differentiate, derivative would be minus x to the power of minus 2 minus 1 over x squared. So this complex fraction simplifies to minus x. I hope nobody has any problem noticing that x squared comes at top. The sign negative remains. And now if you plug in 0, you get 0. Limit of square root of x times e to the power minus x over 2 as x approaches infinity. If you plug in, this becomes infinity. This becomes 0. So it's infinity times 0. Again, I'm going to quickly show you. So what you have is the product of this and e to the power of minus infinity divided by 2. This part is 1 over e to the power of infinity divided by 2, which is 0. Okay. Infinity times 0, we move things around. And I hope everybody can see that it's easy to take this one down and make this positive. Do you follow what I'm saying? The exponent positive. That is the methodology we are going to use here. Now, again, we have worked on this many times. You know the answer is. So we are going to, okay, when we plug in, we get infinity over infinity, which means we're going to use the L'Hopital's rule. And to use the L'Hopital's rule, you take the derivative of the top, you get 1 over 2 squared of x. Again, you may have to show that by now. We've done it many times, so that's okay. This one, the answer is itself, times 1/2, okay, times 1/2. Again, I hope everybody can see that. So, complex fraction, you multiply these two, and the first thing that happens, the 2 drops. The numerator becomes 1, and the bottom becomes square root of x times e to the power of x over 2. Now, if you plug in infinity, I hope you recognize that when I plug in infinity, this is infinity, the product infinity, 1 over infinity is 0. Okay. So one might say, infinity times 0 is 0. That's not true. Sometimes it doesn't happen that way, okay? So you have to show, you have to work it out. Indeterminate differences, type of infinity minus infinity. Try to convert the difference into a quotient by using a common denominator or rationalization or factoring out the common factor. So what we have, an indeterminate form of 0 over 0, infinity over infinity, if possible. Okay, that's what you try to do if that is possible, everybody. If it's not, then it's not. the limit of cosecant x minus cotangent x as x approaches 0 from the right. 0 from the right. Notice we can write this as, if we plug in, by the way, we get infinity minus infinity. Here's the reason. Cosecant of 0. Remember, cosecant is 1 over sine. Cotangent is cosine over sine. As x goes to 0, sine goes to 0. So when the denominator goes to 0, they both go to infinity. Cosecant and cotangent are both infinity. So we have infinity minus infinity in this case. Again, I'm assuming that common arcs, we are comfortable with them and we know what's going on. And reminding you that we should know that sine. Well, let me write it here. Sine of 0 is 0. Okay. All right, so plug in, so change it to 1 over sine and 1 over, and sine over and cosine over sine. So you can take a common denominator of sine x. So if I take a common denominator, it becomes 1 minus cosine x over sine x. And now I can plug in. So let's write it here. I plug in, I get 1 minus cosine of 0 over sine of 0. Cosine of 0 is 1. So I get 0 over 0. That means I can use the L'Hopital's rule. That means I'm going to differentiate the top and the bottom as follows. This gives me 0 minus, cosine gives me negative sign. This makes it positive sign. Sine gives me cosine. And now I plug in 0. If I plug in 0, I get sine of 0 over cosine of 0. And that is 0 over 1, which makes it 0. It's important to know that it is 0 over 1, everybody. And therefore 0. 0 over 1, and therefore 0. Let me erase this part. Can keep the rest. All right, so if I plug in 1, everybody, I get ln1 minus ln1. And please understand, I mean ln of 0 minus ln of 0. So this is from the right. So this becomes ln of 0 from the right minus, if I plug in 1, the same thing, ln of 0 from the right, which means each one is negative infinity. Minus infinity minus negative infinity. I want to make sure we understand why. So this is minus infinity minus, and that makes it what? Minus infinity plus infinity, or infinity minus infinity. That makes it indeterminate form. Therefore, what is the technique? Reminding you of logarithmic properties, we can put them together using the quotient rule. So this is ln of x to the power of 7 minus 1 over x to the power of 5 minus 1. So we use this quotient rule and we put them together. It's that simple, everybody. And so Let's plug in. If I plug in, if I plug in 1, this becomes what? 0. Ln of 0 from the right. This becomes ln of 0 from the right. Let me just write that for everybody. I plug in 1 from the right. 1 from the right causes to get ln of 0 from the right over ln of 0 from the right, and each one is negative infinity over negative infinity, and that means I can use the L'Hopital's rule. By the way, you can interchange. You're taking the limit, you can take the ln out, put the limit in, and you're taking the limit of this expression. So how do you take the derivative of that? You plug in. If I plug in 1, I get 0 over 0. So ln of 0 over 0. So over here, I can use L'Hopital's rule. So I get the natural log of this limit. So natural log of this is 7x to the power of 6. This is 5x to the power of 4, everybody. Now, if I plug in 1, top becomes 7, bottom becomes 5. So I get 7 over 5 here. Natural log of 7 over 5, whatever it is. This is an exact answer. You don't have to take it, you calculate it to approximate it, or you don't even have to write ln 7 minus ln 5, okay? So it's pretty straightforward, everybody. Find the limit of secant x minus tan x as x approaches pi over 2 from the left. And again, even if you don't know secant, we know it's 1 over cosine, and cosine is 0 when we get close to pi over 2. So 1 over cosine or secant x is infinity, and it depends from which side. Pi over 2 from the left, that means the first quadrant. Imagine pi over 2 is 90 degrees, so pi over 2 from the left, like 89 degrees. So it's positive, okay, class? So positive infinity minus tan x, the same thing. And let's say tan of close to pi over 2, 89 degrees, that's infinity. So this is infinity minus infinity, okay? And secant x, okay, secant x goes to infinity. Tan x goes to infinity as x goes to pi over 2 from the left. So the limit is indeterminate form, infinity minus infinity. And so what do? We rewrite this as 1 over cosine, and this one as sine over cosine to take a common denominator. Becomes 1 minus sine over cosine. Now, if we plug in, what happens? If you plug in pi over 2, sine of pi over 2 is 1. So let's just do that. So you get 1 minus sine of pi over 2 over cosine of pi over 2. And sine of pi over 2 is 1, cosine of pi over 2 is 0. So you get 1 minus 1, 0 over 0. And that means you can use the L'Hopital's rule. That means I'm going to differentiate the top and the bottom as follows. 1 goes away. Negative sine gives me negative cosine. Positive cosine gives me negative sine when I differentiate. So that means now I am looking at, you can say, there are two ways to do that. You can say this is the limit of cotangent x as x approaches pi over 2 from the left, and you may know that cotangent of power 2 is 0. Or you can plug in and say negative cancels out the negative. You no longer need the limit, and you write cosine of power 2 over sine of power 2, which makes it 0. Either way is fine. So the final answer is 0. Either way you look at it. Change it to cotangent x, cotangent of power 2 is 0. Or just plug in just the way it is, you get minus cosine of power 2, which is 0, over sine of power 2. Okay, the negative signs cancel each other. Indeterminate powers. Several indeterminate forms arise from the limit of f of x to the power of g of x as x approaches a. If both of them are 0, we get 0 over 0. If one of them is infinity, get infinity to the, if this one is infinity, this one is 0, we get infinity to the power of 0. And if this one is 1, we get 1 over infinity or negative infinity. All of them are considered indeterminate, everybody. Each of these three cases can be treated either by taking the natural log, let y be f of x to the power of g of x, and then ln y is g of x times ln of f of x. So limit of ln y as x approaches a is k. Then limit of ln of f of x to the power of g of x as x approaches k becomes, as x approaches a becomes e to the power of k, if you go that route. Or by writing the function as an exponential format. So you can write this e to the power of ln of f of x times g of x. So it becomes e to the power of g of x times ln of f of x. In either method, we are led to the indeterminate product of g of x times ln of f of x. Okay, either here or here. And you see the power of k, which is of type 0 times infinity or infinity times 0. So we have to tackle those types of problems as well. Let's look at an example. The limit of 1 plus sine of 4x to the power of cotangent of x as x approaches 0 from the right. So please understand, if I plug in 0, sine becomes 0, so I have 1. If I plug in 0, remember cotangent of 0. By the way, the graph of cotangent, remembers, almost looks like, remember the graph class, that helps. Okay, this is x equals 0. X equals pi. This is power to 0. Okay, so from the 0 goes to infinity. So it's 1 to infinity, 1 to the power of infinity. And again, the reason, I mean, this is a horrible graph, but you get my picture. The idea is that if you want to remember this stuff, make sure you remember the basic graph. It gives you the domain, range, intercepts, if they have vertical asymptotes, horizontal asymptotes, whatever information you want, you have to know the graph. Everything is here. Otherwise, you have to memorize what's the intercept, what's the domain, what's the range, and so forth. From the graph, I can get all of those. Okay, let me erase this. So this is 1 to the power of infinity, okay? And because the bottom is a function, so is the top, in other words, the base and the exponent, I'm going to take a natural log. This is one way to do that. So let y represent this expression. And if I take the natural log of y, cotangent becomes the coefficient. ln of the right side, cotangent becomes the coefficient, so sits in front. Remember that this is the power rule. And I'm going to write this over tan x because cotangent is 1 over tan x. So cotangent x next to this is the same as under the fraction bar denominator. And so we are going to work on this. We're going to take the limit of this. And whatever the answer is, remember, the answer to the question becomes e to that power. So we're going to take the limit of ln y as x approaches 0 from the right. It was given 0 from the right. So again, tan x, remember tan of 0 is 0. Sine of 0 is 0. So the numerator, if you plug in everybody, if you plug in, you get ln of 1 over tan of 0. ln of 1 is 0. Tan of 0 is 0. 0 over 0. We can use the L'Hopital's rule. So we are going to use the L'Hopital's rule, everybody. That means I'm going to differentiate the top, I'm going to differentiate the bottom. So to differentiate the top, since it's a natural law, flip this over. Let me just do it on the side and then put it there. 1 over 1 plus sine of 4x times, now the derivative of the inside, sine gives me cosine, but 4x gives me 4. So this would be the numerator, the denominator is secant squared. Okay. And let me erase my work again. So let's plug in 0 for sine, cosine, secant. Let's see what we get. Everything, every x is replaced by 0. 4 times 0 is 0. You know cosine of 0 is 1, so 4 times 1 is 4. You know sine of 0 is 0, so that's 1. And you know secant of 0 is 1 over cosine. That means 1 over 1, that means 1. You square it, you get 1. And so you have a 4 divided by 1. So the answer is 4. Again, I'm assuming everybody is very comfortable with trigonometry and so on. So what is the answer to the question? E to the same power. So this original question is the limit of y as x approaches 0 from the right, and y is the same as e to the power of ln y. Class y is the same as e to the power of ln y. And we proved for ln y, we ended up with 4, so this must give us e to the power of 4. Section 4.5, summary of curve sketching. Definition, vertical asymptote, short VA, horizontal asymptote, short HA. When you have a rational function, RF, short for rational function, f of x is in the form of n of x over d of x. The numerator, a sub n, x to the power of n all the way to a sub 0, and the denominator is b sub m, x to the power of m all the way to b sub 0. Both of them must be polynomial, which means n must be positive, n must be a whole number. So n of x and d of x are polynomial. D of x can't be 0, and the domain is all real numbers except what make the denominator 0. Vertical asymptote, x equals a, if the limit of f of x as x approaches a from the left or from the right is either negative or positive infinity. The graph of a rational function never crosses a vertical asymptote. It may intersect its VA. Simplified in lowest term, no common factor. VA would be d of x equals 0, x equals a. Meaning, first thing first, you make sure this is in its lowest term before you move on. Sometimes there's a common factor between the top and the bottom. that results in a hole rather than a vertical asymptote, okay? So limit of f of x as x approaches a, or a from the left or a from the right, any of them is positive or negative infinity, VA has the equation x equals a. Horizontal asymptote, or HA. Horizontal asymptote HA of a curve y equals f of x is y equals L if the limit of f of x as x approaches negative or positive infinity is L. That's the definition of a horizontal asymptote. The graph of a rational function may or may not cross a horizontal asymptote. HA has the definition limit of f of x as x approaches positive or negative infinity is L and y equals L. Horizontal asymptotes occur when the degree of the numerator is less than or equal to the degree of the denominator. I hope you remember this from pre-calculus. So here's the definition of oblique asymptote. OA, or slant asymptote, the equation is of the first degree, y equals mx plus b, if the limit of f of x as x approaches negative or positive infinity is mx plus b. So these are definitions, everybody. Now, how do we find them nice and easy? For vertical asymptotes, set the denominator equal to 0. If n is less than m, that means the degree of the numerator is less than the degree of the denominator, horizontal asymptote becomes y equals 0. If n is equal to m, horizontal asymptote becomes the ratio of the leading coefficients, a sub n over b sub n. If n is precisely m plus 1, meaning the degree of the numerator is larger by only 1, you divide by long division, synthetic division, you name it. It gives you a quotient mx plus b, which is of degree 2, and a remainder. This quotient, y equals mx plus b, is the oblique or slant asymptote, everybody. That's how you find it. We have the function f of x equals x squared minus 4 over x minus 1, and we want to find all asymptotes. Vertical asymptote x equals 1, because all you have to do is set the denominator equal to 0, right? Remember the easy way out. Set this equal to 0. That gives you the VA. The degree of the numerator is 2. The degree of the denominator is 1. 2, this is 1. I hope you realize x to any power, there is no power, that means 1. Because the difference is 1, we don't have a horizontal asymptote, but we do have a slant asymptote, and we can do a long division or synthetic division, either way. So I'm assuming you can do both of them. So when we divide the top by the bottom, we get x plus 1 with the remainder negative 3. So we're going to write this. F of x is x plus 1 plus negative 3 over x minus 1. Again, notice, just for the sake of argument, x squared divided by x, just to remind you, you divide by the first term, you get x, and then you multiply by these 2, you get x squared minus x. You subtract. These 2 cancel each other, and this becomes positive. You bring this one down, you divide this one by this one, you get 1, you multiply the 1, and then you subtract again. So this is how you arrive at the answer. Slant asymptote, y equals x plus 1. It's that simple. All right, sketch the graph of f of x equals x minus 1 over 2x plus 1. And we know how to do it from pre-calculus. We just add a little bit more for calculus, such as finding where the function is increasing, decreasing, and so on and so forth. But the basics are the same, starting with the intercepts. So you want the x-intercept, set y equal to 0. A fraction is 0, so you set y or f of x equal to 0. The fraction is 0 when the top is 0. So when you set this one equal to 0, everybody, when you set this one equal to 0, that means x minus 1 is 0. And that means 1 comma 0. For the y-intercept, you set x equal to 0. So set x equal to 0. So if I replace the x with 0, I get negative 1 over 1. So I get 0, negative 1. So those are very simple. I hope everybody's okay with those. And we can plot those. So we have 1, 0. Now we want 0, negative 1. Okay. Asymptotes. Start with the simplest one. VA, 2x plus 1 equal to 0. That means x equals negative 1. So the denominator is 0. That gives you the VA. Horizontal asymptote. The degree of the numerator is 1. The degree of the denominator is 1. So 1/2. Y equals 1/2. So that's your vertical asymptote. And y equals 1/2. And there is no slant asymptote. Again, why is this the answer? Degree of the numerator is 1. Degree of the denominator is 1. So the leading coefficients take over. X over 2x becomes just 1/2. So y equals 1/2. And there is no slant asymptote. So y equals 1/2. And by the way, asymptotes are dashed lines because they are not part of the graph. Rather, they help us graph the function. Derivatives and domain. First of all, domain is all real numbers except what makes the denominator 0. That means get rid of negative 1/2. So x can't be negative 1/2. How do you write it in an interval format? Negative infinity to negative 1/2 union negative 1/2 to infinity. That's how you would write it. So we are practically done with pre-calculus. There's one more step. I'll explain it in a moment. But now, and that is really good enough to graph. Just I want to let you know that if what we did in pre-calculus, we have all asymptotes and then say the vertical asymptote cuts this one into 2 subintervals. It may be 2 vertical asymptotes and gives us 3 subintervals. In every subinterval, we need points. In this subinterval, we have it. So these 2, that really gives us this one. Over here, it's either like that or like that. But it can't be like this because that means I need another x-intercept, so it must be like that. Just to give you an idea, you should know how the graph looks like, just for the sake of argument. But aside from that, so we want to go with f prime of x and work on other things. F prime of x, this is f over g, so let me erase my word. Let me write this as f over g. And write down I need f prime g minus g prime f over g squared. Okay, so we need 1 times 2x plus 1 minus 2 times x minus 1 over 2x plus 1 squared. That's the idea. And so simplification of the numerator will result in 2x plus 1 minus 2x plus 2, and we end up with 3 in the numerator. Now, before we move on with the sine graph, please understand this is always positive. And the reason it's always positive because the numerator is positive and this is being raised to the power of 2 is positive. The only time it's not when the denominator becomes a 0, which means that x equals negative 1/2. So when I say it's positive, almost always. So maybe I should erase that because I don't want you. But generally speaking, this is positive. So meaning it's always an increasing function. And the way we would write it is not from negative infinity to positive infinity, but rather we would write it in its domain. So it's increasing in its entire domain in like this. But if you were to do the sign graph, you pick a number to the left of negative 1/2, for example, TP. We would pick negative 1. To the right, 0 would be the easiest. And if you plug in 0, you get 3/1 squared. If you put -1, whatever this one is the square, it becomes positive. So both sides is positive. So it's always increasing. There is no local max or mean. There's no extrema. So it's increasing in the entire domain. Okay. And if we want to differentiate it again, because of the inflection point and concavity, we are going to rewrite this as 3 times 2x plus 1 to the power of -2 for the sake of differentiation again. And so I'll show you, and then again, I have to erase it. So if I want to differentiate this, I'll do that. To get f double prime, I get 3 times -2 times 2x plus 1 to the power of -3 times the derivative of the inside, which is 2. So we have 3 times -2 minus 6 and 2. The product is -12. This goes down, make it positive exponent. And I hope you recognize that actually at x equals -1/2, things change. And if we go with the sign graph, to the left of -1/2, again, let's pick the test points over here, -1, over here, pick 0. And if you plug in -1, this becomes negative cubed, negative, never negative over negative is positive. If you put 0, this becomes what? Negative over positive is negative. So that means it's positive, f double prime is positive from -infinity to -1/2, concave up. Over here, from -1/2 to infinity, f double prime is negative, it's concave down. Now, the inflection point can happen at -1/2. However, -1/2 is not part of the domain, therefore there is no IP. One more time. If the function was defined at -1/2, you would put it in there and find the y coordinate, and that would be the inflection point. It's not, because it's not part of the domain, and that's why we don't have an inflection point. Now, the next thing is to check, always check if the function crosses the horizontal asymptote. And by the way, we know the horizontal asymptote has the equation 1/2. We have to set this equal to 1/2 and work it out. So we set the function equals y equals 1/2 and work it out. So we do the cross product. Let me erase my work again. So you multiply these two, you get 2x plus 1. You multiply these two, you get 2x minus 2. And I hope you recognize this means -2 equals plus 1. -2 equals 1, which is impossible, and that has no solutions. This is phi, everybody. Greek letter phi, which represents no solution. We're done. We don't even need an extra point, because again, we should know this is clearly the answer. And the reason we should know this is the answer, because if it were here, see, it's one of these. I needed another x-intercept, but I pick up an extra point, x equals -1/2, let's say -1. If I put -1 here, -1 and -1 is -2. 2 times -1 and 1 is -1, and the ratio is +2. So plug in -1 into the original function. Plug in this -1 into original function, and that's the point. This is the graph for that part. This is the graph for this part, and we are done, everybody.